The Yukawa theory describes the interaction between fermions through the exchange of a scalar boson. Its interaction Lagrangian is written as. Notice the analogy with the Lagrangian we had to describe the interaction between bosons, scalar bosons. The reason why we have psi bar psi and not just psi squared is because psi bar psi is a scalar, and therefore it's the right way to build a Lagrangian, which has to be a scalar quantity at the end. As in the case of the phi-4 theory, Feynman diagrams can be used to describe basic processes using perturbation theory. So in the case where the coupling constant G is small, but now the Lagrangian is not the same, and therefore the Feynman rules are not all the same. In fact, what changes is the vertex and the lines connecting the vertex. Because we have 3 fields here, the vertex will only connect 3 lines and not 4 like in the phi-4 theory. And one of these lines is a boson, a scalar boson, while 2 of these lines have to be fermions. So the dashed line represents the scalar boson phi. And in order to distinguish between psi bar and psi, we are going to have an arrow pointing toward the vertex and one pointing outward the vertex. And now the value of the vertex is minus Ig. So as an example, let's consider the scattering of a proton with an antiproton. We have 2 tree diagrams contributing to this amplitude in the lowest order. So let's calculate the second diagram as an example. So we labeled each line with their 4 momenta, and we have 2 vertices. We don't account for the propagator of the external line, but we have one internal line, so we need to write its propagator. We need to sum over the momentum for the internal line. And we have energy momentum conservation at each vertex. The first delta function kills the integral and changes q into k1 plus k2. We then recognize that the second delta function is just a global energy momentum conservation, which we don't need to write explicitly. In principle, for the amplitude to be physical, it should not depend on epsilon. Therefore, we need to see under which condition epsilon can be neglected and taken to 0. For this, we need to choose an inertial frame where we can express the component of the 4 momenta, and it's natural to choose the center of mass frame. By definition of the center of mass, the sum of the momenta is 0. Therefore, we have, if we have p for the proton, we have minus p for the antiproton. And because they have the same mass, if they have the same magnitude of the momenta, they necessarily have the same energy. Therefore, k1 plus k2 is simply equal to 2e for the time-like component and 0 for the space-like component. If the mediator of the interaction is lighter than twice the mass of the proton, this denominator will never be 0, and in this case we can get rid of the I epsilon. But if this is not the case, then we can have potentially a division by 0. This means that when 2e is equal to the mass of the mediator, we have a huge amplitude for the process. And that's actually how we discover new particles, is by colliding 2 known particles with enough energy to produce new particles which could act as their mediator. And we will see when that happens a resonance in the probability for the process or the associated cross-section. The overall behavior of the cross-section as a function of the energy depends on different things like the other diagrams, as well as kinematic prefactors in front of the probability. However, this resonance behavior is clearly due to this diagram and occurs when the mediator is produced on mass shell. and that's only possible when it's a heavy particle which is created, which is heavier than the sum of the mass of the incoming particles. Uh, Now we could ask, why do we have something which is still finite and doesn't diverge to infinity because we have a division by zero? In fact, this is because we used the propagator for the mediator, assuming that it was a free particle, like a particle which would not be able to decay. Indeed, we won't show it, but if we were to account for the possibility for the boson to decay, that will introduce additional term in the denominators, imaginary term, proportional to the width of the resonance, or inversely proportional to the lifetime of the particle, and which will naturally allow us to take I epsilon equal to 0. But of course, if a stable particle were produced, it will not be able to decay, and therefore we will have a problem. However, it turns out that there is no such a thing as a stable scalar spin-zero particle. The lightest spin-zero particle we know of is a pion, and it's unstable. The pi naught, for instance, decays into 2 photons. Therefore, there is no such a thing as a spin-zero particle which does not decay into lighter particles. And we will always have a resonance when we produce these scalar particles, which will be with a finite width.